All right, good morning, everybody. I've started recording so we can go ahead and get started. It's 11 o'clock and time to begin. Before we get started, just a couple of announcements, or if you will. First off, regarding your test, um, I've graded 3 of the 4 problems. I still have to grade the last problem. But unless something unexpected comes up, I will get that done this afternoon. I can't tell you for sure what time I'll get the grades posted in Canvas, but could be late this afternoon, could be this evening, could be tomorrow morning. I don't know, but I should finish grading this afternoon. So just be on the lookout sometime later today or tomorrow. Should have grades, and I'll also post a solution to the test. All right, so I reckon that's the big announcement as far as just in general. What we're going to do today is continue talking about how to construct shear and moment diagram. So we did a couple of examples yesterday, and keep in mind, or I'll remind you, this is using what I call the graphical approach. So we're not actually determining equations, but we're using some, I don't know, I hesitate to call them tricks, but we're able to draw those diagrams using other means. And I did want to point out, if you haven't looked through the book or read through this section in the book, there's a pretty good detailed procedure. I think it would be beneficial to you to maybe read through that and see how he explains some of those things. I'm pretty sure I got the page number right. If I looked it up correctly yesterday, it's on page 273 in your textbook. You'll see a nice detailed outline procedure. Read through that. Again, if nothing else, he might explain things in a slightly different way. Might make more sense to you. Also, as usual, there's lots of good examples, and it's almost impossible for me in the time we have to draw a shear moment diagram of every possible scenario you might encounter. So look through the examples in the book. It's very likely you might see some examples there. Might have something that we don't do during class time. So look at those in the textbook. All right, so one of the things I mentioned yesterday was how do we know, when we're constructing our moment diagram, say using the shear diagram, how do we know, what shape the graph is? Is it linear? Is it a straight line? Is it going to be curved? And so that's what I want to talk about first, and then we'll go through and work another example. But here's where we're going to use those relationships. There were 2 of them from yesterday. I told you I'd use these again. And here's where I'm going to use them again. Right? We had this relationship that remember, W here is the distributed load. We saw that it was equal to the negative of the derivative of the shear function. Now, that tells me something, and think to, just in general calculus, when you take the derivative, in particular, when you take the derivative of a polynomial function, what happens to the largest exponent is it decreases by 1. Right? When you take the derivative, you multiply by the derivative and then you subtract 1 from the derivative. So you get a function that's 1 degree lower than the original function. So if the distributed load is equal to the derivative of the shear force, then I know the shear force curve or graph is 1 degree higher than the distributed load. And again, this would be, we're just looking at polynomial functions. And that's typically what we're going to see. We're not going to see any weird, strange functions. They're going to be defining our distributed load. So they're going to be nice, smooth, maybe constant, linear, quadratic. It's a nice, smooth function, polynomial. So I know that the shear diagram, when I graph that, it's going to be 1 degree higher than the distributed load. We also had this relationship that V was the derivative of the moment function. So a similar thing, if we're just talking about polynomial functions, that means my moment curve is 1 degree higher, being lazy here, than the shear. That's how I knew when I was drawing the moment diagram yesterday that the moment diagram was linear, because the shear was constant. It's always going to be 1 degree higher. So let's just look at some kind of generic examples here. So what if our distributed load is 0, right? We just have a concentrated force. So we just have P. So we've got a beam, something like this, where we don't have a distributed load, we just got a concentrated force. Well, what that's going to mean, right, when we draw the, let's see, we'll put some support there. Gotta have something holding the beam up, right? So when we draw the shear diagram, right, we know from yesterday we're going to start at whatever that support reaction is, right? And it's constant until we get to that force, and it goes down, and then it'll go back across. But if our distributed load is 0, our shear diagram is going to be constant, and our moment diagram is 1 degree higher than constant, so that means it's going to be linear. That's how I knew when we drew those diagrams yesterday that the moment diagram was linear, because I know it's 1 degree higher than the shear force, right? And again, just some other sort of illustrative examples. What if we have a constant distributed load? So here we got some distributed load, and it's constant. And we'll keep the same. We're going to have support reactions, and that's going to tell me where my shear diagram is going to start at, where that support reaction is. But if the distributed load is constant, my shear force 1 degree higher is going to be linear. And so this again would be linear. And my moment diagram, 1 degree higher than linear, would be quadratic. So it's going to be a curve. And it's going to be a quadratic, 1 degree higher. And let's do one more. Let's look at if we have a linear. So here we got a distributed load that's linear. So my shear diagram now is 1 degree higher than linear. It's going to be quadratic. And I don't know. It's going to be curved, right? And this is my shear. And the moment 1 degree higher than quadratic would be cubic. And I don't know, y'all may be much better than me. If you're just drawing a general quadratic or cubic, they're curved. That's the best I can do. I mean, I can't distinguish between, look at a curve and tell you if it's quadratic or cubic, especially if I'm drawing it. I can't draw the difference. But I do know it's 1 degree higher than quadratic is cubic, so it's going to be curved. Now, a couple other observations, but first, questions at this point about how we know what the shape of those graphs are going to look like. Okay. Well, one, we've kind of already been taking this for granted, but formally sort of show why it's true. V is dm dx. That's the derivative of the moment function, but that's also the slope of our moment curve. If you look at the graph, right, that's what the derivative is. It's the slope. So if v is positive, so if v is positive, that means the slope of the moment curve is positive. That means it's increasing. Right? So this means our moment is increasing. And that's, again, we kind of did this before. I just kind of sort of told you, if the area was positive, we were going to increase. And if the area down here was negative, we were going to decrease. But this is why, mathematically, that's the way it works. Again, since v is the slope, positive slope is going up, you're increasing. If v is negative, if your slope for m is negative, that means m is decreasing. Right, so the moment's going to go down. Just looking at this one, for example, where this v is negative, we're going to go down. Now, if v is 0, right, that means the slope of the moment is 0. And you should know that from calculus, that's basically the first derivative test. That's how you identify local maximums and minimums, right? If the slope is 0, that's going to occur where v is 0. That's why when you look at these diagrams I drew, right, those 2 points line up where this would be where you would have a 0 slope. Likewise for this one, kind of pretend like it's 0 there. Slope is 0. All right. So that's where you're going to get your local minimum or maximum. All right. Any questions about that? Now, there's one other thing we need to do, because some of you may be thinking or wondering. Yeah, I drew this quadratic and this cubic. How do we know that it curves like this, concave down, as opposed to not being concave up? Well, that's the last thing, kind of in general, we're going to look at. And right, so if v is equal to dm dx, then if we take the derivative of v, that would be equal to the second derivative of our moment function. Now, you might remember, hopefully you do from calculus, something called the second derivative test. Right, the second derivative tells you concavity. So if dv dx is positive, right? Again, dv dx is the second derivative of our moment function. Also, Remember, that means if dv/dx is positive, that means v is increasing. So if v is increasing, the second derivative of our moment is positive. That tells you our moment is concave up, shaped like that. So if the velocity, not velocity, I've been too much dynamics. V, the shear force, if it's increasing, our moment's going to be concave up. And conversely, if dv/dx is negative, that means our shear force is decreasing. The second derivative of the moment is negative. That means it is concave down. It'll be shaped like that. That's how I knew when you go back and look at these examples, look at this one. Here, the shear force V is decreasing, so it's concave down. Same thing here, V is going to be decreasing, it's concave down. So that's how you tell, whether if it's curved, whether it's concave up or concave down. Just look at, is the shear force increasing or decreasing? All right, so with that, now we should have everything we need to construct any shear and moment diagram. Again, just using what we've talked about the last day or two. Again, basically, we calculate our support reactions, and we should be able to draw this diagram with minimal. We might have to calculate some area, do some basic math, and subtract some numbers, but that's all it requires. We don't have to go through and actually get the equations for V and M. All right, so any questions at this point? We're going to work one more example, a little more involved than the two we did yesterday. So speak up if you don't want me to change, get a clean sheet of paper. Everybody done with this? Okay. All right, so let's see if we can. We're going to draw the shear and moment diagram. And let me draw this. Got this beam. Got pin support at this end. We've got a distributed load. £120 per foot. And it's constant. Mine looks like it's kind of sloping down there, but it's supposed to go straight across here. It's constant. And then right at the end of that distributed load, we also have a concentrated force here. So this is 100 pounds. And that is just a concentrated force located right at the end of that distributed load. And then we've got another distributed load over here, also constant. Also 120 pounds per foot. And we've got roller support under our beam, supporting this beam right there at that end where that distributed load starts. We'll call this B, C, and we'll call this ND. Now we just need some dimensions. This is 2 feet from A to B, and 2 feet from B to C, and 2 feet from C to D. So we've got a 6-foot long beam supported with pin support at the left end A. I got a roller support here at C. And we got 3 loads applied. These 2 distributed loads and then this 1 concentrated force. I think I've got all my loads and my dimensions. And so we want to construct or draw the shear and moment diagrams for this beam. Again, what that does is shows us what the shear force and bending moment are for any cross section down the entire length of that beam. And that's what we would have to do if we were trying to analyze this beam and calculate the maximum stresses. All right, so we obviously got some support reactions. We'll call this AY. The pin support could provide AX, but it's going to be 0, so I'm going to not write it on there. Again, all of these examples at this point, we have no axial loads. There's no force in the x direction, so AX is 0. And we have a vertical support reaction there at C, we'll call CY. And we need to determine what those 2 support reactions are, because we need those to draw our shear diagram. So to get that, we need to replace these distributed loads with the equivalent resultant force. Right? And the equivalent resultant force for distributed load is just equal to the area. So this is constant, it's a rectangle. Height times width, 120 times 2, be 240 pounds. Right, and that would act at the centroid of that area, which for a rectangle is right in the middle. Right, so that, my writing's not real great. That would be located right in the middle. If it's 2 feet long, it'd be at 1 foot. Same thing over here. It's 240 pounds. It's, again, height times width, 120 times 2. And it's going to act right in the center as well. It would be right in the middle if that's 2 feet long. And we need to do that when we apply our equilibrium equations. Right? So when we sum the moments, I'm just going to sum the moments about A, set that equal to 0. And we should be able to find what CY is. So we've got CY times, it's like that's 4 feet away from point A. And we've got this 240 pounds causing a clockwise moment. So minus 240 times 1. We've got the 100 pounds causing a clockwise moment. So minus 100 times 2. And then finally, this 240 pound equivalent force. 240 looks like 5 feet away. And so I think I've got everything. And we solve for CY. And if I did my math correctly, I got 410 pounds for CY. Right. Anybody see anything wrong with that? Does that look okay? Comments, questions? And now, sum the forces in the y direction. And we can do that and calculate what AY is. So I got AY going up. I got CY going up. And then I got the 240 going down. 100 pounds going down. And then 240 going down. All that's got to add up to 0. Solve for AY. And does that look correct? Anybody see anything wrong there? I got 170 pounds. So I know AY here is 170 pounds. All right, so we should be good to go now as far as drawing our shear and moment diagram. But before we start in on that, again, any questions how we got our support reaction? right? So again, typically what's done, and it kind of helps you, line things up, is we draw our shear and moment diagrams directly below our beam. And let's see, try to draw a straight line across here. So this is going to be our shear force diagram. Now here we do have numbers and we have units, and you only have to put it once. You don't have to put it beside every number on this diagram. As long as you've got the units given one time, that's sufficient. And I'm gonna label these points again to kind of help us keep lined up where we're at along the beam. All right, so now we're ready to draw our diagram. So I know from yesterday, hopefully you remember, the shear force at the end is going to be whatever that support reaction is. So it's going to start here at 170 pounds. Now, here's an important thing, because I see students do this quite frequently. We replace this distributed load with that equivalent force when we apply these equilibrium equations to calculate those support reactions. But that distributed load is not the same as a 240-pound force concentrated at that one point. They're equivalent, but they're not equal. So when we draw our shear diagram, we've got to draw it with the distributed load on there. We can't say, okay, I'm going to come straight across here 1 foot and then go straight down 240 pounds. Doesn't work that way. Right? We just talked about first thing this morning. It's 1 degree higher. So if W is constant, our distributed load is constant, our shear is going to be linear. Now it's going to go down a total of 240 pounds. So when we get to B, right, we're going to go down 240. So 170, if we go down 240, that would be what, minus 70? But it's going to be linear, right? To get from here to there, it's linear. We don't go straight across, go straight down 240 and then straight across. Right? But we do, again, we're going down what that equivalent force is, but how we go down, again, is not the same as if we just had a concentrated force right in the middle. All right, everybody clear with that? And I'll point out, my graph is not going to be to scale. I can hear that already. All right, but everybody good so far? All right, well now we're at B. We've got this, we do have an applied concentrated force. It's acting down, it's 100 pounds. So we go straight down 100. So we'd be at minus 170 now. So that's no different than what we did yesterday. We got that concentrated force. We go up or down, whatever that force is. In this case, 100 pounds acting down, we go straight down 100. So now we're located here. Now between B and C, there are no forces. So it stays constant between B and C. Just go straight across, does not change. No increase or decrease. Now at C, we can't forget we've got this support reaction, a concentrated force. This one's acting up. So we're going to go up 410. So if we were start out down here at minus 170 and we go up 410, that's going to put me at, if I added that right, 240. So here we're going straight up. Yeah, that's not straight. 410, that concentrated force going straight up. now from C to the ND, we've got this distributed load again. Just like over here, we're going to go down a total of 240 pounds. This is constant. So 1 degree higher than constant is linear. So it's going to be linear. And that puts me back to 0, which is a good check, right? Because again, here we're going down a total 240. So if we were at 240, that puts me at 0. Well, the end of this beam is free. There is no shear force acting on that free end of the beam. So if we had not wound up at 0, we know we've made a mistake. So there is my shear diagram with, again, no calculations other than just some basic math to construct that based on our beam with our loading. Any questions? Now we got our shear diagram. I can look at this diagram and tell you what the shear force is anywhere along that beam. If I want to get the maximum shear stress, then I want to use the maximum shear force, which, looking at this diagram, looks like that'd be our maximum, 240. So that's what's going to cause our maximum shear stress. Right? So now we continue. And we're going to come down right below that, and we're going to draw our moment diagram. Again, we need units, but we only have to write them once. Moments here, our forces are in pounds, and our distances are in feet. So these are foot-pounds or pounds-feet. If you draw me a diagram and you don't put units on there, I'm going to take off a point. Each place you don't put units. Now, if you remember from yesterday, how we get the moment, how much it increases or decreases, is based on the area that's under the shear diagram. So this is, we use the shear diagram to construct the moment diagram. So we need to calculate the area. Well, in order to do that, right, we need to know what this area is, and I'll call it A1. We need to know where this crosses. Right? I need to know what that distance is. And it's not necessarily going to be right in the middle. This is where you'll see my picture is definitely not to scale. If I drew it to scale, you would see, because I've got 170 and 70 about the same distance. Where it crosses would be much closer to the right side over here than where I've got it crossing. So we've got to calculate what those two distances are. I'll call this A2. So we need to know, again, where does that thing cross? Because I've got to have that in order to calculate the area. It's a triangle, 1/2 base times height. I know the height of both of those, but I need to know what the base is. Now, we could do this several different ways. I think one of the easiest ways is to use similar triangle. So if you look at this big triangle here, and again, keep in mind my picture is not to scale. This is 170 and that's 70, so this is what, 240? And this is a total of 2 feet across here, right, from here to here. So I want to know if this is 170, what is that? That's what we're trying to calculate. What is this distance x right here? And so again, this is one way to do it, is to use similar triangles. I know x is to 170, S2 is to 240, and x is, I got 1.417 feet. So again, obviously my picture not to scale there. But this is 1.417 feet. If you subtract that from 2, that means this is going to be 0.583 feet. Right. Any questions how I got the location where that shear graph crossed the axis? All right, but now we can calculate our area. So I know A1, that's 1/2 base times height. Well, the base is 1.417. The height is 170. And this is positive, right? The moment's going to increase by this amount. I got 120.4. Again, it's positive. That's how far it's going up. Let's go ahead and calculate A2 while we're at it. Now, it's negative. Again, it's a triangle. 1/2 base times height. Here the height is 70. So this comes out to be negative 20.4. Right, now, when we draw this, again, I'll remind you what we talked about yesterday. If we look at the end of this beam, there is no moment at the end of that beam. Right? There's no fixed support there, it's a pin support, so we don't have a reaction moment. There's no applied concentrated moment there. So the moment is 0 at the end of that beam. So it starts here. Again, maybe I should label my points again. It starts here at 0. It's going to go up 120.4. And also what we talked about a minute ago, these should line up. Now where we hit our maximum should coincide with where it crosses. This is linear. This is going to be quadratic. 1 degree higher. V is decreasing. It's concave down. So we're going to have a quadratic that's going to reach its maximum right there where V is 0. And again, it's curved. I can't draw it, differentiate between a quadratic or a cubic, but it's going to be curved and it's going to be concave down. Now A2 is negative. We're going to go down 20.4. V is still decreasing, so it's still concave down. So when we get here, again, this is where my picture not being to scale and going to affect our graph looks. But this is, I didn't label, this is 120.4. We go down 20.4, that puts me at 100. So again, the area is how much you go up or down on your moment diagram. So we go down 20.4, puts me right here at 100. Next, we've got this big rectangular area here, called A3. Right, it's negative. We're going to go down whatever that area is. And it's a rectangle, height times width, 170. And from B to C, this is 2 feet. So 170 times 2, 340. So we go down 340. So if I'm at 100, I go down 340, that's going to put me at negative 240. Now, what the graph looks like, we got to go back and look and see. Remember, it's 1 degree higher. Here, V is constant. 1 degree higher than constant is linear. So this is going to be a straight line. Going from there to down here minus 240. That's linear. And finally, we got one more area. Now, we know, just looking at our beam, just like the moment being 0 at the left end, the moment better be 0 at the right end as well, because we have no moment at the end of that beam. But always check yourself, right? So don't just assume that you've done everything correct, right? We're going to check, calculate what that area is and see verify that it does take me back to 0. So A4, it's positive. We're going to increase by that amount. It's a triangle, 1/2. On the base here, this is 2 feet. And the height is 240. So indeed, that is positive 240. So we're going to go up 240, which does indeed take me back to 0. Now, what the graph looks like, here we go. The shear force V is linear. 1 degree higher than linear is quadratic. It's decreasing, so it's concave down. So it's going to be a quadratic, a curve that's concave down, goes from the minus 240 to 0. And we have just constructed our moment diagram. The process is not that difficult. And for what's involved, it's pretty simple, basic math. It just takes practice. It's the way with most anything. The more you practice, the better you will get at this. And so with enough practice, you could take this, hopefully, construct this shear moment diagram, in just a few minutes, as opposed to having to cut it 3 times and calculating what your equations are and then graphing those functions. This is a much shorter, quicker, easier way to do it. Any questions about this one? This is, again, how I expect you, if I ask you on a test to draw a shear moment diagram, this is what I'm looking for. I want you to use this method to do so. All right. Any questions? Anything related to shear moment diagram? All right. Well, then we got a few minutes to just kind of take about 5 minutes or so and kind of give you an introduction to what we're going to spend tomorrow doing. This you'll find in section 6.3 and 6.4 in your book. And again, I highly encourage and suggest that you read the book. But what we're talking about here is calculating what we call bending stress in beams. We call it bending stress, but you'll see as we get further into this, what this is, it's a normal stress. This is a stress that's going to be normal or perpendicular to the cross section. Just like, we calculated normal stress in axially loaded members. Well, you'll see when we bend a beam, we create normal stresses in that beam. But unlike, when we had an axially loaded member, like say this pin, I'm either pulling on it in tension, and the normal stress is going to be in tension, or if I'm pushing in on it on each side, I have a compressive normal force causing a compressive normal stress. You'll see when we bend something, we get both tension and compression. And so again, just real basic introduction here today. We'll get into actually deriving this formula tomorrow. But let's say we got a beam, and it does not matter what the cross section looks like. I'm just drawing it rectangular because that's easy to draw. But the cross section could look like anything. Again, make sure we establish orientation of our coordinate system. So we've been using X as the axial direction. That's not going to change. Y, we're going to call the vertical direction. And if you look at that cross section, the horizontal would be the Z direction. Right? And this beam's got some length L. And we apply a bending moment to this thing. What's going to happen, this thing, if we apply some moment Yeah, I'll draw it this way. It's going to bend. And not great. But if we apply a bending moment in this direction, it's going to bend. I don't know how well this will show up or do, but I have a ruler, and I don't know, maybe I'll turn it this way. If I apply a bending moment, you see what happens to the ruler. It bends, right? It deforms, changes shape. It's not straight anymore. Now, when we do that, that's going to cause, if we look at, in this case, if I'm bending it this way, the left side of this ruler is being stretched. It's going to be in tension. The right side is being compressed. It actually gets shorter and it's in compression. And so there's going to be, if you look longitudinally down this beam, there's going to be one surface that does not change length. And that's called the neutral surface. So again, basically all we're doing today is getting a little terminology out of the way. So this is called the neutral surface. Yeah, there's no change in length. If this beam starts out with some length L, that is still going to have some length L. I'll call this LT for L top and LB for bottom. So if we bend it this way, that distance got to get shorter. And think of, like you look at a circular arc length. Closer you are to the center, the shorter distance. The further you go out, the longer the arc length. So that's going to be shorter than the original length. And the bottom is actually going to be longer. It's going to stretch. So the top is going to be compressed. And the bottom is going to get stretched. So anywhere above that neutral surface is being compressed. It's getting shorter. It's going to be in compression. We're going to have a compressive normal stress. Anywhere, in this case, below that neutral surface, it's getting stretched. And so it's going to have a tensile normal stress. Now, just note that the opposite would be true if we bent it the other way, right? If we applied a bending moment and bent it this way, then just the opposite would happen, right? The top up here would be in tension and the bottom would be in compression. And then you would have your neutral surface there where it's not being stretched at all. So it depends on which direction your moment is, which way you bend it, but one half's going to be in tension, one half's going to be in compression. And if you look at the stress distribution, this will be the last thing we'll do today and we'll stop. You just look at a 2D and we're actually going to go through and sort of prove this tomorrow. But if we got this beam and we apply a moment this way, we've got, this would be our neutral surface. And from here on out, I'm going to abbreviate neutral surface as NS, so I don't have to write that out all the time. That would be our neutral surface. But the length does not change. If we bend it this way, that top is going to be in compression. And we're going to find out tomorrow that this is going to be linear. The bottom down here would be in tension. Right? So this is going to be in tension. It's going to be in compression. Stress is going to be zero here on the neutral surface. It's not being stretched or compressed. And again, don't worry, we're gonna prove this and verify this tomorrow. Last term to be familiar with, if you look at the cross section, so assume it's rectangular again because it makes it easy to draw. So if we're looking at the cross section rather than the beam from the side, again, that x-axis coming straight out at you. This is y and this is z. And up here, we would have compression. Down here, we have tension. This axis, the z-axis, where, again, the stress is going to be 0, we call this the neutral axis, which from here on out, I'm going to call NA. So the neutral surface, we're looking longitudinally down the beam. It's the surface that doesn't deform. It's where the stress is 0. If you're looking at the cross section of the beam, that axis where the stress is 0 that separates tension and compression, we call that the neutral axis. So you just need to be familiar with that terminology. And so that's what we're going to do tomorrow. We'll start right here. And we're going to try to come up with a formula that will calculate, we can use to calculate what that normal stress is. That's the topic for tomorrow. But between now and then, you need to be practicing drawing not free body diagrams, shear moment diagrams. Tomorrow we'll return our attention to calculating a formula for normal stress. All right, so that's where we're stopping. Any questions? Anything anybody wants to ask right now before I stop recording? As always, if you got a question, after I get through stopping recording here, if you hang around, I'll be glad to discuss anything with you.